Greetings, one and all, and welcome to this lecture that introduces you to waves. Right, waves. We're not actually going to deal explicitly with water waves. I just really like this picture. We are going to start with a disturbance on a string. So because of the internal forces, if we create a disturbance, that pulse, we call this the pulse, moves down the string. Now note that the pulse is not really a physical thing. It's a pattern that moves down the string. What's going to happen if we wiggle our hand up and down continuously? Take a guess. So from playing around with this when you were a kid, you might have predicted this pattern, which should look very familiar to you. Depending on where we put our vertical axis, we're going to get a cos or sine graph. So a sinusoidal function. Okay, so this is a sinusoidal pattern, and that is the wave that we're going to be dealing with, that arises from this oscillating disturbance over here. So we want to model this wave, this sinusoidal pattern. So we're going to stick down a set of axes. Okay, can anyone tell me what are the labels on the axes here? What is your intuition about the label of the axes? Okay, they're both going to be position, because what we've done here is we've taken a snapshot or a photograph of this pattern. It's moving to the right, the disturbance is over here, and we've taken a snapshot. I get to make my favorite noise. Okay, we've taken a photograph of this pattern, and therefore we can stick down axes that have to do with the y position against the x position. We're also going to be concerned with the actual rope particles. We'll get more into detail about that later. And as you can see, the velocity of this wave is to the right. So here we have a snapshot of our wave taken at a particular point in time. So we can imagine this is our rope. And you can see the axes are measured in meters. So they deal with position or length. And if I ask you to identify on this graph one cycle of the pattern, can you do that quickly? Pause the video and identify one cycle of this pattern. Right, welcome back. So hopefully you should say, well, this pattern starts repeating itself there. Then it starts doing exactly the same thing. So that is one cycle of this pattern. And we call that one cycle of the wave pattern the wavelength lambda. Okay. If we start from here, that would be a wavelength from there to there. That's when it starts doing the same thing again. Okay. So this is our new Greek letter for the week, lambda. And you can write it like this, lambda, lambda. Write a couple of lambdas for yourself. You should have a pen and piece of paper in front of you. The Greek letter lambda. So if lambda meters is the distance for one cycle, write the mathematical expression for this graph. Ooh, wow. And there's your hints. Remember that for simple harmonic motion, we said a cos of the time divided by the period, and that was one cycle times 2 pi. So see if you can write the mathematical expression for this graph over here in terms of lambda. Pause now. Right, welcome back. So hopefully you should have said my amplitude is A. This is a sine graph that I'm dealing with, positive sine graph. And I want to tell my calculator that I know that my calculator understands 2 pi to be one cycle, and I want to tell it that I want to take this fraction of one cycle, where one cycle is lambda. So my variable here is x. So for example, if we put x is equal to lambda at that position over there, that's telling my calculator, or it's telling this cos function, that at that point I've done lambda over lambda, i.e. one full cycle, or 2 pi radians. Okay, so x over lambda, the fraction of one full cycle, where one cycle in meters is lambda meters. Okay, I'm going to write that in a more familiar form. So a sine 2 pi over lambda x. And I'm going to write it now in even more compact form. I'm going to write it as a sine kx, where k is called the wave number and is simply equal to 2 pi over lambda. K is a shorthand way of writing 2 pi over lambda. So K is called the wave number and it's equal to 2 pi over lambda, but please, danger, gevaar, pas op, ingozi. You have been dealing with K for the last few weeks as the spring constant. Yeah, do you remember Hooke's law? F is equal to minus Kx, where K is the spring constant. In what are the units of the spring constant again? Newtons per meter. Yeah. And you know that the angular frequency can be written as the square root of the spring constant divided by the mass. It's a very different thing to the wave number. Yeah, the wave number has to do with wave motion, not with a spring. So it's got nothing to do with a spring. When we write the equation for a wave or a snapshot of a wave, when we're talking about that K is 2 pi over lambda. It's a very different and separate thing from the spring constants. I'm very sorry that they used the same constants in the textbooks, but that's what they use. So please just beware when you see K in the context of wave motion, it's a very different thing from K in the context of a spring and the spring constants. Okay, here we have a snapshot of a wave, a few new terms for you. We call the top of the wave the crest and the bottom of the wave the trough. There you can see from there to there would be one cycle, so we call that one wavelength. Can you tell me which equation you would use if you were to mathematically model this snapshot of the wave? Okay, so in these equations, the angular frequency and the wave number are constants. Which would you choose? Pause now. Okay, hopefully a nice easy question. So you're looking for a positive sine graph and you're looking for y as a function of x. Y as a function of x. We've been dealing with x as a function of t for a long time, yeah? But now this mathematical equation, we're dealing with y as a function of x. Where k, just a reminder, is called the wave number and it's 2 pi over lambda. All right, so this little exercise should be familiar to you from before, except now we've got a cos function which is relating y as a function of x. And remember that our wave number k is simply 2 pi over lambda, so we can write the function like that. I would encourage you to write it like that. And our lambda, remember, is the distance for one cycle, yeah, of the wave pattern. So if I was to make k larger, what happens to this cos graph again? If I make k large, I squish it up. Yeah. And also if I make k large, what happens to lambda? If I make k large, lambda must get smaller. As I make this denominator smaller, this gets larger. So there's my smaller wavelength. Yeah. And similarly, if I make k smaller than what it is in this scenario over here, then I stretch out my cos graph. And if I have a smaller k, that means I have a larger lambda. Can you identify lambda on this graph? Do that quickly. Pause the video, please. Right, welcome back. So you should be able to see that the pattern that you're looking at that's going to repeat is all the way from there to there, yeah, before it starts repeating. So that would be lambda in this case. All right, a couple of quick, easy questions. There's our general equation, and if I give you a specific value for k over here, can you tell me what the wavelength of that wave is, please? Pause the video now. Come back, so you should have got pi meters. All right, let's delve a little deeper into what happens to the particles or the rope particles on the rope. Now, this isn't an actual physical particle. It's just a very, very small segment of the rope. And we call that small segment of the rope a rope particle. And I like to give my rope particles names, so I'm going to call this very small segment over here George. So I'm asking, a pulse over here approaches George from the left. And can you please tell me what is going to happen to George? So pause the video and commit yourself to an answer. Pause now. And welcome back. So you were looking for D. Yeah, we're going to have a look at this in more detail now, but it's very important to realize the rope particles, even though this pulse is moving to the right, the rope particles simply move up and down. Because of the internal forces between the particles in the string, the pulse moves to the right-hand side. So we can see this pulse over here moving to the right-hand side. But because of the forces between the rope particles, the way that those act out is for the rope particles simply to move up and then to move down. So once again, the wave is moving to the right. So these pulses over here, the sequence of pulses we call the wave or the wave pattern. It's moving to the right. The wave is moving to the right, but the rope is moving up and down. And the name we give to a wave where the direction of motion of the wave is perpendicular to the movement of the particles, we call that a transverse wave. So we can imagine rope particles in the transverse wave as moving perpendicular to the wave, and we can imagine rope particles at any point in this wave. Yeah, there's Tembakazi, there's Shahida. All of these rope particles are simply going up and down as the wave moves past, yeah, as these pulses move past. All right, wave motion is perpendicular to the particle motion for a transverse wave. And you can think of, in the case of a slinky, one of these links in the slinky. If you look closely at one of these links, you can think of that as a rope particle. What does it do? It just moves up and down, but you can see that the pattern or the pulse here, it moves to the right. Yeah, you can see it moving to the right, but each particle you can think of in the slinky is just going up and down. So if you have enough data, I encourage you to Google PHET, P-H-E-T, simulation wave on a string, and you should come to this particular simulation, and then just play around with it. Yeah, there are a couple of settings that are particular for what I'm going to demonstrate to you in the next slide. So I've said that this must oscillate over here. I've said that it must not be fixed over here. It must have no end, right? So unfixed. I've reduced the damping to 0, and I've put it in slow motion. And if you do that, then you should get something that looks like this. There it goes. Okay, so we've got a sinusoidal pulse over here, which is creating a sinusoidal wave pattern. And the wave pattern is moving to the right. Everyone agrees. But now have a look at one of these green beads, or these green rope particles. What's happening to them? Just going up and down. Yeah, as the wave pattern moves to the right, the rope particles are simply going up and down. All right, just for interest's sake, I can also introduce you to the idea of a longitudinal wave, and that's when the direction of the wave and the movement of the particles are actually in the same plane. Okay, but here's a rather beautiful example of air molecules, for example, would be an example of this, where the wave pattern, which in this case you can see there would be a pattern. Okay, so there's a pattern which is moving to the right. So the pattern is moving to the right, but if you look at any one of these dots, any one of the black dots, but a couple of highlighted in red, you can see they're simply moving slightly to the left, slightly to the right, slightly to the left, slightly to the right, but the pattern seems to move to the right. Okay, so once again, very important, that idea of the wave. The wave is just a pattern. It's not a thing. Yeah? The things, the particles are moving slightly to the left, slightly to the right, but the pattern, what we identify as the wave, that's what's moving to the right. How would you model mathematically this motion of George? So he's going up to some maximum position and then down to some negative maximum position and then back up to some maximum position, and he keeps on passing y is equal to 0. What sort of graph would you use to model that motion? Hopefully you said that you would model it using a sine graph, yeah, or a cos graph. So now we have a graph which models George, which is a sinusoidal graph, and it's telling us how George's position, y position, is changing with time. but we also have the snapshot of the wave, which is y against x, and that's also a sinusoidal function. Whoa! So we got lots of different sinusoidal functions here, which are meaning very different things. So we're making this transition from simple harmonic motion into waves. So here's our good old mass on a spring, and we can model the back and forth motion over there. Do you remember what these axes over here would be? This is the x position of the mass, and this is what the x position is doing in time. It's going from a maximum to a minimum, etc. And we can model it, in this case, using a cos function. Now we're speaking about waves. So the wave that we're going to be most interested in is what I can produce on a rope by wiggling my hand up and down. And we create the sinusoidal pattern that moves to the right-hand side. Hopefully you've tried this at home. So if we take a snapshot or a photograph of this wave at a particular time, we can model that snapshot also as a sinusoidal function, a cos function. So can you tell me what go on these axes over here? What goes on those axes? You remember on this vertical axis, it's the y position and that's the x position. We're talking about the vertical distance here, the distance from there to there of the actual rope, and similarly the horizontal distance. Okay, so these are both cos graphs over here, but they give us very, very different information. And you should remember that omega is 2 pi over the period. And what is the period again? The period is the time it takes for one cycle. So that's the period over there. Whereas k over here is called the wave number. What is the wave number equal to again? K is equal to 2 pi over lambda, where lambda is one cycle of this pattern from there to there. So there is our snapshot, okay? And we can model that snapshot as a graph of y against x using a sinusoidal function, a cos graph, or a sine graph. Now I want to focus on this particle over here. I'm going to call this rope particle George. So what is George doing again? George is simply moving up and down, right? How would you model George's motion, this motion up and down? Does it remind you of anything? Well, hopefully it reminds you of simple harmonic motion, yeah? So instead of a mass or a particle moving horizontally back and forth on a spring, here we have a rope particle that's moving up and down, yeah? So if you were to look at how this motion unfolds in time, it would look like that, right? So the y motion of George, if we assume that George starts at the top at t is equal to 0, George moves down, and then he moves back up to his maximum position, and then down, etc. Yeah. So once again, we have two similar looking graphs that give us very different information. This is a snapshot of this wave pattern that's been taken at a particular time, and this is the motion of one particular rope particle and what that rope particle is doing in time. Yeah? So this is the motion of George as time ticks by. So we've got a mathematical model for a snapshot of the wave. That's y as a function of x at a particular time. So t is constant. And we have all the information about the y position of all the different rope particles at that particular time. Yeah? So George over here we know is at y is equal to 0. Shahida over here we know is at y is equal to 1. And Tembakazi, she's the rope particle over here. We can see that at t is equal, let's say this was t is equal to 0. At this particular time, Tembakazi was at y is equal to 2. We've also got a model for a particular particle in the wave. Yeah? So now if we analyze, for example, here, let's say that George is sitting over here actually. So if we analyze the motion of George, so George at t is equal to 0 is sitting at y is equal to 2, right? So at t is equal to 0, George is sitting at y is equal to 2. And then as time ticks by, George is going to go down and then back up and then down. So here we have information about the y position of George, and only of George, and how that y position changes in time. A quick question for you, a snapshot of a wave. So this is a y versus x at a particular time. We're told that this happens at time t is equal to 0. The photograph is taken. George is sitting here at x is equal to 0, right? There's George. And we want to know which of these graphs correctly represent the change of George's y position with time. Pause now. Welcome back. Okay, so you should have said C, because at t is equal to 0, George starts from this position over here. Just to make sure we're making physical sense of this, if I extend this wave pattern like this, can you see that as this moves to the right, this side of the hill, George is going to start sliding down this side of the hill. So this downward motion of George's y position over here in time corresponds to him sliding down the hill as this part of the wave pattern moves past x is equal to 0. Right, here's another snapshot with George still located at x is equal to 0. Give this one a go. Pause now. Welcome back. So you should have said D. So this snapshot is taken at t is equal to 0. So at t is equal to 0, we see that George's y position is 0. So that means that we've narrowed it down to A or D. That satisfies both A or D. But if we're told this wave is moving to the right, that means that this valley over here starts moving past x is equal to 0, where George is. So as time goes on, George is going to start sliding down that valley, which means that as time moves on, George's y position is going to start increasing in the negative direction. Okay, so if we start with this equation, just remind me, what does this equation describe again? This is y as a function of time. It's a sinusoidal function. I've written as 2 pi over the period multiplied by t. This equation describes the y position of a rope particle and how that changes with time. So it's describing the motion of a rope particle. What does t mean in this situation? Well, t is the period. So what's the definition of the period? It's the time it takes to complete one cycle. So in this case, it's the time it takes for a rope particle, for example, George, to complete one cycle. So what exactly does that mean in this situation? Well, let's have a closer look at George. I'm going to name this particle over here George. Can you tell me what is the period in this case? If we start our stopwatch now, that means the period is the time it takes to get back now. And there's another period. Okay, so it's the time it takes for George to complete one full cycle of down and all the way back up to its starting point where the motion starts to repeat itself. The time it takes for a rope particle to complete one cycle is called the period. The wave equation, the equation climax of the lecture. So you should recognize this over here as a snapshot of the rope, y is a function of x, whereas y is a function of t. You should now recognize as the simple harmonic motion of a rope particle. We can combine these two equations to get the wave equation, a sine kx minus omega t. The minus is for a wave traveling to the right, and we have a plus for a wave traveling to the left. I'll give you an intuition about why this is a minus for the right in a few slides time. But let's just make sure that we can explain to our grandmother what this equation means. This is telling us the y position of any rope particle, i.e. for any x position along that rope at any time. There we go. Grand, this gives us the information about the y position of George or Tembakazi or Shahida at any time. A new bit of vocabulary for you in this brackets over here. This is called the phase of the wave. of the wave equation. And just a reminder that the wave number 2 pi over lambda and the angular frequency 2 pi over the period. Okay, so here we have a wave traveling to the right, so we can model it using the wave equation. So this is the wave equation for a wave traveling to the right. It has the minus sign there. And I said that this equation gives us the y position of any rope particle, so for any x position, at any time. Okay, so let's have a closer look at that. So here I have two axes. What are the labels going to be? Y versus x, okay? And I'm going to put down some x positions here. Now, which of these red particles would you like to call George? Let's say this is George over here, okay? So George is at 0.5. So if we were to say x is equal to 0.5, we could find out the y position of George, if 0.5 was here, for any time t. Yeah? So as t is ticking by. So there's t is equal to 0, 1, 2, 3, 4. For any of those values, if you were to substitute those values of time in here, for x equal to 0.5, for a given amplitude, you would be able to find the y position, yeah, of George. Or if we were to substitute x is equal to 1, then we'd find out the y position of Shahida for a particular time, you know, depending on what time you took your snapshot. And similarly for Tembakazi and for Carl over here and for Louis, for all of them, we could find their y positions for particular x values at particular times. Right, let's do a quick example. A wave is traveling to the right. It has an amplitude of 1 meter, wavelength of 2 meters, and a period of 2 seconds. Please write the wave equation for this wave. Pause the video now. Welcome back. So you should have got that. There's your amplitude of 1 and your pi x and minus pi t come from the fact that you had a wavelength and a period of 2. All right, and the minus sign means moving to the right. Okay, what is the y position of the rope particle located at x is equal to 0.5 meters at t is equal to 0 seconds? Pause the video here. Welcome back. So that was a simple substitution, 0.5 in there, 0 in there, and you should have got 1. Yeah, so that's the y position of George if George is located at 0.5 meters at the snapshot taken at t is equal to 0 seconds. So let's have a closer look at that. So can you guys draw a graph of the snapshot at t is equal to 0 seconds? Yeah, so can you draw that graph over there? Pause the video now. So your graph should look like that. So it's a graph of y against x. So there's no time information here. Yeah, we know that t is equal to 0. So this is what our rope looks like at t is equal to 0 if we take a photograph. All right. Now, can you guys locate George on this graph? So where's George located? In this example, he's located at x is equal to 0.5. Okay, so x is equal to 0.5, and at t is equal to 0, where is George sitting? Hey, he's sitting at y is equal to 1. There we go. All right, so you can see what that information means here. Next question, what is the y position of the rope particle located at x is equal to 0? So let's call that rope particle Tembakazi. So Tembakazi is at x is equal to 0. At t is equal to 0.5 seconds, where is Tembakazi? Pause the video now. Welcome back. So a simple substitution once again, x is equal to 0, t is equal to 0.5. You put that into your calculator, you should get the y position out as -1. Let's dig a little deeper. So if x is equal to 0, if we substitute x equal to 0 here, we get this equation out, right? Can you guys draw the graph, please, of y against t? Pause now. Right, welcome back. So your graph of y against t should be this negative sine graph. And remember, the question asks us, what is the y position of the rho particle located at x is equal to 0 at t is equal to 0.5? Now this graph is drawn for Tembakazi. Yeah, we said, look, we're only interested in Tembakazi. So we substitute x is equal to 0 into here. And the equation that we get out is the y position at any time for Tembakazi, for x is equal to 0. Yeah? So at t is equal to 0, Tembakazi was at the origin. But this graph is telling us that at t is equal to 0.5, where's Tembakazi? She's moved down, and she's at a y position of -1. All right. Excellent. Well done. We'll see you in the next lecture. Right, a quick example for you. Remember, George is at x is equal to 0, and this wave is traveling to the left. Pause now. Welcome back. So you should have got A. Yes, if you're confused, please go to the discussion forum immediately. Right, let's link these graphs to the wave equation. So what's the general wave equation for a wave traveling to the left? Do you remember? Okay, it's kx plus omega t. Yeah, and I've taken this to be sine. It could also be cos. So let's just check this out. If you were to write this equation for t is equal to 0, so substitute t is equal to 0, and what equation do you get out? And then substitute x is equal to 0 and see what equation you get out. Write those two equations down quickly. Pause now. Okay, welcome back. So you should have got these two equations. And now you should be able to see how they relate to these graphs. Yeah. So remember, this was the snapshot taken at t is equal to 0 for a wave traveling to the left. Well, there's our equation for a wave traveling to the left. Okay, and if I substitute t is equal to 0, I get y as a function of x. Yeah, sine kx, positive sine graph. There it is. Yeah, there's the positive sine graph, y as a function of x. And similarly, if I substitute x is equal to 0, that's George's position, x is equal to 0, I get a graph y as a function of t, a sine omega t. So I get a positive sine graph out here. Yeah. So there's your sort of correspondence or physical intuition of why we have a plus here. For a wave traveling to the left, we need to get out a plus sine graph for George's motion, yeah, a positive sine graph. For a wave traveling to the right, I don't know if you remember from a few slides back, but for a wave traveling to the right, for that particle located at x is equal to 0, we actually got a negative sine graph out. Yeah? So for a wave traveling to the right, we had a minus there, which would give us a sine of minus omega t. If you remember from school, that's the same as minus a sine omega t. So you can check through that for yourselves for the problem a few slides back. Write out the general wave equation for a wave traveling to the right, and then get out your specific graphs for t is equal to 0, for x is equal to 0, and make sure that they correspond to the snapshot and to the motion of George. And a last quick problem for you to try. There's your general wave equation. Pause now, give this a go. Pause now. Welcome back. Right, so you should have got D. It's a little bit of a trick question because what it was asking you to do was to look at your phase over here and see what information you had from this graph over here. Now this is a snapshot, so you actually only have information about the wavelength, that 2 pi over lambda, which is that k, the wave number, 2 pi over lambda, that coefficient of x. So you actually have no information about the angular frequency. In other words, the period. Yeah. So you can ignore your coefficient for t. You're only interested in your coefficient for x. And you can see here the most squashed up graph is the red one. So that has the highest wave number, and the most stretched out is the green with the lowest wave number 2. That's all for now. Signing out. We'll see you in lecture 2.